for quite some time. He has worked as dean as well as director over here at Goel Institute. Those of you who might not know, so we welcome you once more, and we are looking for a very fruitful session. Welcome.
थैंक यू सर। मतलब मेरे यहाँ तक पहुँचने का बहुत बड़ा योगदान है और मुझे सर के साथ काम करने का अवसर भी मिला हुआ है। प्रॉब्लम है तो हो सकता है कुछ आवाज में प्रॉब्लम जा रही हो, लेकिन मुझे लगता है जो मैसेज मैं देना चाहूंगा वो क्लियर कट जाएगा उसमें प्रॉब्लम नहीं होगी। थैंक्स फॉर योर नाइस इंट्रोडक्शन। मेरा तो रियल टाइम सिस्टम्स पे है और मैं क्योंकि बेसिकली इलेक्ट्रॉनिक्स फील्ड से हूं तो मैं कोशिश करूंगा कि मैं टॉक को एप्लीकेशन पे ज्यादा फोकस करूं कि रियल टाइम एप्लीकेशंस को कैसे यूज किया जाता है। मैं एक एरिया माइक्रो कंट्रोलर एम्बेडेड सिस्टम्स है जो कि रियल टाइम सिस्टम्स में हम लोग यूज बहुत करते हैं उसको, तो मैं उसके प्रोग्रामिंग पोर्शन पे फोकस करूंगा। हाँ, लेकिन इसमें जरूर करूंगा कि जितने भी एप्लीकेशंस एरियाज हैं उस पर मैं फोकस कहाँ कहाँ हम रियल टाइम सिस्टम्स को यूज करते हैं और उसकी क्या प्रॉपर्टीज होनी चाहिए और कैसे हम उसको आज की डेट में और कौन कौन से नए टूल्स अवेलेबल हैं जो कि रियल टाइम सिस्टम्स में हम यूज कर रहे हैं। सो आई एम नाउ स्टार्टिंग द सेशन। Trying to focus on these topics: introduction of real-time systems, what is real-time, how we differentiate between real and logical time, and applications of the real-time systems. What is the basic model of real-time system? What should be the characteristics of the real-time system, time task, and safety and reliability. And in safety and reliability, I will not go in details. Rather, focus on the safety critical systems which are developed in formal development. So first, I will start by giving the introduction. The commercial usage of computer dates back to a little more than 60 years. It can roughly be divided into mainframe, PC, and post-PC areas of computer. Was marked by expense that quite unaffordable by individuals, and each computer served a large number of users. The PC era saw desktop easily be afforded and used by individual users. Seeing emergence of portable computers and computers embedded in everyday applications, making and several computers every day. Applications in the first two computing era were rather rare and restricted to applications such as space and defense. In the post era of the use of computer systems based on embedded technologies have already touched every facet of our life and is still growing at a pace that was never seen before. Embedded processing and internet devices have now captured everyone's imagination. They are just a small fraction by real-time systems. If we casually look around us, we can discover many of them. Often they are looking devices. We can notice several gadgets and applications which have today become indispensable to our everyday life, are in fact based on embedded real-time systems. For example, we have ubiquitous consumer products such as digital cameras, cell phones, microwave ovens, telecommunication domain products, and applications such as set-top boxes, cable modems, applications, office products, printer security systems. We encounter real-time systems in hospitals in the form of medical instrumentation and systems. A large number of equipments and gadgets based on real-time systems, which thought not used quickly, but nevertheless still important to our daily life. Internet routers, base stations and cellular systems, industrial plant automation systems, industrial robots. That in recent time, computers have become application areas. At present, the computers used in real-time applications vastly outnumber the computers. Okay. Am I audible?
यस सर, आवाज आ रही है।
शो कर रहा है कि नेटवर्क प्रॉब्लम में तो लिखा है।
वीडियो ऑफ कर दीजिए सर आप।
ठीक
जी जी
हाँ ठीक। At present, real-time applications vastly outnumber the computers that are being used in conventional applications. It is true that an overwhelming majority of the all processors being manufactured are getting deployed in the real-time applications. What is more remarkable is the unmistakable trend of steady rise in the fraction of the processors manufactured worldwide finding their way to time applications. Some of the phenomenal growth in the use of real-time systems in the recent years, manifold reduction in the size and the cost of the computer, improvement to the available computers at rapidly filling size, reduced weight, rapidly shrinking sizes, and their increasing processing power have together contributed to the scenario. Not too far back were considered expensive to automate and now be affordably automated. For instance, when my processor costed several tens of thousands of rupees, they were considered to be too expensive to be put inside a washing machine. But when cost only a few hundred rupees. Their use deploying real-time technologies has been matched by the growth of real-time systems. Real-time notion of time. Whenever we quantify time using a physical clock, we do with real time. An executive notion of time can be of an automated chemical plant. For example, reaction can check a certain predetermined temperature, say to 50 degrees centigrade, automatically switches off the heater within a predetermined interval, say within in the description of part of the time value that was referred to denotes the reading of some physical clock present in the plant automation system in country, which is also known as actual time, deals with the qualitative notion of time. Relations such as before, after, sometimes, eventually, precedes, succeed, etc. Logical time reading from a physical clock are not necessary for ordering the event. Consider the following part of the behavior of a library automation software used to automate the bookkeeping activity of a library. After a query, book is given by the user. Details are displayed by the software. In this, the and display of results are logically ordered in the terms of events. Follow the wide of any real-time considerations. We are now in the position to define what is a real-time system. When we need quantitative expression of time to describe the behavior of the system. In this definition of it is all carried out using a physical clock. It automatically switches off the heater within, say, 30 milliseconds is clearly an example of real-time system. Description of partial behavior of a system. The can be described by listing its response to various external stimuli. All the clauses in the description of the behavior of a real-time system involve quantitative measure of time. That is, the description of the behavior of a system means quantitative expression of time. Real-time systems. Described without using any quantitative expression of time is of not a real-time system. try to present application of real-time systems from different but application area of real-time systems. Chemical plant, control and data acquisition system. Process conversion in an chemical plant, a real-time computer that based on current reading of pressure, temperature, and chemical concentration of the reaction chamber. Based on the automation system decides on the instant to maintain the chemical reaction at a certain rate. Each time, the automation system should decide on the exact instantaneous corrective actions required, such as changing the pressure, temperature, or chemical concentration, and carry out actions within certain predetermined time bound. Typically, in a chemical plant, control application ranges from a few seconds to milliseconds. The is automated car assembly plant. Automated car assembly plant. This plant that is car moves on a conveyor belt as shown in the figure. Stations are placed. Each station has specific work on the product, such as fitting the engine, spray painting the car, etc. as it moves on the conveyor belt. And the first workstation on the conveyor belt. Out after the work product goes past all the workstations. It is the arrival of the next product. And begins to perform its work on the work product. In the workstation computer is the workstation must complete its work before the work next workstation. Hundreds of milliseconds. And is supervisory control and data acquisition. SCADA is control systems being used in many industries. Number of distributed events of interest. sensors are scattered at various geographic locations to these data are then processed at and time database that is the current state of the environment. The database is the model of the updated state environment is an energy management system. To carry out load balancing in an electrical energy distribution network. The energy management system senses the energy consumption at the distribution points and computes the load across different phases of power supply. It is the load that monitors and controls traffic depending on the sensed load in different segment of the network. The SCOM makes the router changes its peak routing policy dynamically. The in such a SCADA application is that the sensor must sense the system in regular intervals. Before the next state is sensed. Another example I have taken from the medical application. Systems are robots, robot used in recovery of discharged radioactive material. Is a robot used in repairing radioactive materials.
I would request all the participants to kindly be patient. Due to some network congestion, sir has lost his connection. Please cooperate with us, and I request all the participants to be patient and please wait for sir so that he can rejoin the session. We are trying to reconnect him. Till then, please kindly be patient and please kindly cooperate with us. I request all the participants not to leave this meeting. Just trying to reconnect. There is some network congestion. He is not able to reconnect with us. Kindly be patient till then and kindly cooperate with us. We're trying our level best to join the as I request all the participants to kindly be with us and be patient. I request all the participants to kindly stop their video. Dilip sir, We are sorry for the inconvenience caused. I request all the participants to kindly cooperate with us.
आ रही है बिजनेस?
हाँ सर, आ रही है, आवाज आ रही है।
तो कहाँ से डिस्कनेक्ट हुआ था, मैं फिर वहीं से शुरू करूं?
यही सो लगा।
यही से ठीक है, चलिए। तो हम लोग मिड वाले पे, जो मुझे यहाँ से आवाज गायब हुई थी, तो रियल टाइम एप्लीकेशंस जो मेडकल में हम लोग यूज करते हैं, MRI scanners, radiation therapy equipments, bedside systems, computerized axial tomography, robots, etc. तो जो एग्जाम्पल मैंने यहाँ पे लिया वो है रोबोट यूज्ड इन रिकवरी प्लेस्ड रेडियोएक्टिव मटेरियल्स, बिकॉज रोबोट्स आर nowadays very popular in the medical applications in retrieving displaced radioactive materials. Radioactive materials such as cobalt and radium are used for treatment of cancers. At times during treatment, the radioactive cobalt or radium gets dislocated and falls down. Since human being cannot come near a radioactive material, a robot is used to restore the radioactive material proper position. The robot walks into the room containing the radioactive material, picks it up and restores it its proper position. The robot has to sense its environment frequently and based on this information, plan it. The real-time constraint on the path planning task of the robot is that unless it plans the path fast enough after an obstacle is detected, it may collide with it. The time constraints involved here are of order of few milliseconds. Next applications are equipments. A few examples of peripheral equipments that contains embedded real-time systems are laser printers, digital copiers, fax machines, digital cameras, and scanners. The example which I have taken here for discussion is laser printer. Most laser printers have powerful microprocessors embedded in to control different activities associated with printing. The important activities that a microprocessor embedded in a laser printer performs include the following. getting data from the communication ports, typesetting, sensing paper jams, noticing runs out of the paper, sensing when the user presses a button on the control panel, displaying various messages to the user. The most complex activity microprocessor performs is driving the laser engine. The basic command that a laser engine supports is to put a black dot on the paper. However, the laser engine has no idea about the exact shapes of the different fonts, font sizes, click, underlining, boldface, etc. that it may be asked to print. The embedded microprocessor receives print commands on its input port and determines how the dots can be composed to achieve the desired document, and manages printing the exact shape through a series of dot commands issued to the laser engine. The time constraint involved here are of the order of few milliseconds. Can anyone from the audience tell about any other peripheral devices which they can add in the list of the real-time peripheral equipments? I have given some names such as laser printers, digital copiers, fax machine, digital cameras, and scanners. Can anyone from the audience add some more examples in the peripheral equipments? Because there is 100 participants are there, no one is examples to it. Okay, joystick. One answer come, that is joystick. Anyone? Shivam Shukla scanner. I think I have already given the name scanner. Okay, now next area where real-time systems are. Okay, bounce. Where used is automotive and transportation. A few examples of transportation applications, Sudhanshu Singh. Okay. A few examples of automotive and transportation applications of real-time systems are automotive, engine control systems, road traffic signal control, high-speed train control, car navigation system, multi-point fuel injection, that is MPFI. Here with the figure, I am trying to give you a schematic of a real-time systems embedded in an MPFI car. So, in the example of multi-point fuel injection system, which I have taken for the automotive and transportation, it is an example automotive control, engine control system. conceptual diagram of a car embedding an multi-point fuel injection system is shown in the figure. An MPFI is a real system that controls of fuel injection and allows it to operate at its optimal efficiency. In older models of car, a mechanical device called carburetor, I think the person car earlier know what is the importance of carburetor, because it was used to control the fuel injection rate of the engine. It was the responsibility of the carburetor to vary the fuel injection rate depending on the current speed of the vehicle and desired acceleration. Here, experiments have suggested that for optimal energy output, the required fuel injection rate is highly nonlinear with respect to the vehicle speed. Also, experimental show that precise fuel injection through multiple points is more effective than single point injection. In multi-point fuel injection system, inject to individual cylinders, resulting in better power balance among the cylinders, as well as higher output from each one along with faster throttle response. Primarily controls the ignition timing and quantity to be injected. The latter is achieved by the duration for which the injector's valve is open, popularly known as pulse width. The sensors are determined by the data gleaned from sensors located all over the engine. These sensors monitor the ambient temperature, the engine coolant temperature, exhaust temperature, emission gas content, vehicle road speed, crankshaft position, camshaft position, and MPFI engine with even at 8-bit computer the job of determining an accurate fuel injection rate for given values of speed and acceleration compared to carburetor system. And system not only makes a vehicle more fuel efficient, it also minimizes pollution by reducing particle combustion. So, take some example of real-time system. I have taken from field. Here also, number of applications available in the telecommunication, such as cellular systems, video conferencing, cable modems, etc. The example I have taken here is a cellular system. A cellular system has become a very popular means of mobile communication. As we know that nowadays it becomes impossible to visualize the life without a cellular system. A cellular system usually maps a city into cells, and in each cell, a base station monitors the mobile handset present in the cell. Besides, the base station performs several tasks such as locating a user, sending and receiving control messages to a handset, track of call details for billing purposes, and hand off of calls as the mobile moves. Call handoff is required when a mobile moves away from a base station. As a mobile moves away, it receives signal strength, falls at the base station. The base station monitors as soon as the signal strength falls below a certain threshold value. It hands off the details of the mobile to the base station of the cell to which the mobile has moved. The handoff must be completed within a sufficiently small predefined time interval so that the user does temporary disruption of service during the handoff. If call handoff is required to be achieved in a few milliseconds. So this is also an example of a real-time systems. Then where real-time systems find applications are aerospace applications. Here it is used in avionics, flight simulation, airline cabin management systems, satellite systems, and computer on board an aircraft. The example which I have taken, computer on board an aircraft. I have tried to take as an example in the different domain of life. Now, in this presentation, I have taken 12 ranging from industry to all walk of life. In aerospace, the example which I have taken is computer on board an aircraft. In many modern aircrafts, the pilot can select an autopilot option. As soon as the pilot switches the autopilot mode, an onboard computer takes over all controls of the aircraft, including navigation, takeoff, and landing of the aircraft. In autopilot mode, the computer periodically sets velocity and acceleration of the aircraft. Later, the onboard computer XYZ coordinates of the current aircraft position and compares them with the pre-specified track data. Before the next sample values are obtained, it computes the deviation from the track values and takes a correction that may be necessary. In this case, the sampling of the various parameters and their processing needs to be completed within a few microseconds. Application of real-time systems are in the field of internet and multimedia applications. In the field of internet and multimedia applications, real applications include and multimedia multicast, internet routers and switches. Video conferencing application, video and audio signals are generated by cameras and microphones respectively. The certain pre-specified frame rate. These are then compressed and sent as packets to the receiver over a network. At the receiver end, packets are ordered, decompressed, and then played. At the receiver end is that the receiver must process and play the received frames at a predetermined constant rate. Thus, if 30 frames are to be shown every minute, once a frame playout is complete, the next frame must be played within 2 seconds. So these type of controls are performed in real time, are in physical time bound. That's why these are the examples of real-time systems. Next area which I have taken is from consumer electronics. In consumer electronics field, applications of real-time systems are available. A few sample applications of real-time systems in are set-top boxes, internet telephony, augment, microwave ovens, intelligent washing machines, security systems, air and refrigeration, eyes, cell phones, etc. The example which I have taken is of cell phone. Cell phones are possibly the fastest segment of consumer electronics. A cell phone at any point of time carries out a number of tasks simultaneously. These includes converting input voice to a digital signal by deploying processing techniques, electrical signals generated by the microphone to output voice signals, and sampling base station signals into the control channels. A cell phone responds to the communication received from the base within certain specified time bounds. For example, a base station might send a cell phone the one ongoing communication to a specified frequency. The phone must comply to such commands from the base within a few milliseconds. So all these applications are time bound. Next example of real-time systems is in the full area of defense applications. The typical defense applications of real-time systems is missile guidance system, anti-missile systems, satellite-based surveillance systems, etc. For example, in system, is one that is capable of sensing the target and homes onto it. Homing is easy when the target emits either electrical or thermal radiation. In a missile-guided system, missile guidance is achieved by a computer mounted on the missile. The mounted computer computes the deviation from the required trajectory and affect changes of the missile to guide it onto the target. Time constraint on the computer-based guidance system is that the sensing and the track correction task must be activated frequently enough to keep the missile from diverging from the target. Sensing correction tasks are typically required to be completed hundreds of microseconds or even lesser time, depending on the of the missile and the type of the target. Besides the areas of applications, already discussed by me, the real-time systems have found numerous other applications in our everyday life also. One such application is a railway reservation system. railway reservation system. A central repository contains the up-to-date data on booking status of various trains distributed across different geographical locations. Customer queue up at different booking and submit their reservation request. After a reservation request is made at a counter, it normally takes 2 seconds for the system to confirm the reservation and print the ticket. The real-time constraint in this application is that once a request is made to the computer, it must print the ticket or display the seat unavailability message before the average human response time. What is the average human response time? From the audience, can I know what is the average human response time? As far as I am concerned, I know it is about 20 seconds. So within 20 seconds, we unavailability message. This application is an example of category of applications that is in some aspect different from the other discussed applications. For example, if the results are produced just after 20 seconds, nothing untoward is going to happen. So this may not be the case with the other discussed applications of real-time systems. But when the real-time systems, when they are safety critical systems, it becomes important they follow the requirements as in the prescribed time limit. As I have almost all the applications are at least one application from each walk of the life, which is used in real-time manner. Applications of real-time systems in different walk of the life. This is not the only applications. You can find number of applications, and if you want to work on them, you can work also, because basically these are the systems which works in a time-bounded manner. So here I am also proposed, because this is I am not proposing, I say, I have taken it from, I have in the lab given the references from where I have taken this. What should be the basic model of a real-time system? So here a basic model of real-time system or prototype of a real-time system is given. So if you look at the figure, the sensors are interfaced with the input conditioning block. At the basic model of the real-time system, basic model of real-time system, the important functional blocks are taken into the consideration. And in this figure, the sensors are interfaced with the input listening block is connected to the input interface. Output interface, output conditioning, interface, the output conditioning, and the actuators are interfaced in a complementary manner. So now we will brief different functional block of real-time systems of completion of the talk. So what is the sensor? A sensor converts some physical characteristics of its environment into electrical signals. An example of a sensor is a photovoltaic cell, which converts light energy into electrical energy. A wide variety of temperature and pressure sensors are also used. A temperature sensor typically operates based on the principle of Doppler. Temperature sensor based on many other physical principles also exist. For example, one type of temperature sensor employs the principle of variation of electrical resistance with temperature called vector. A pressure sensor typically operates based on the piezoelectricity principles. And also pressure sensor based on other physical principles exist. Then comes actuator. An actuator is any device, we can define an actuator is any device that takes its inputs from the output interface of a computer and converts these electrical signals into some physical actions or its environments. The physical actions may be in the form of motions, change of thermal, electrical, pneumatic, or physical characteristics of some objects. A actuator is a motor. Also very commonly used. Besides, several hydraulic actuators are also possible. Signal conditioning units. Signals produced by a computer can rarely be used to directly drive an actuator. The computer signals usually need conditioning. They can be used by the actuator. This is termed output conditioning. Similarly, input conditioning is required to be carried out on sensor signals before they can be accepted by the computer. For example, analog signals generated by a photovoltaic cell are in and need to be conditioned before they can be processed by a computer. The following are some important types of conditioning carried out on raw signals generated by sensors and digital sensors generated by computers. Voltage amplification, voltage level shifting, frequency range shifting and filtering, convert. Now comes the interface unit. Normally, commands from the CPU are delivered to the actuator through an output interface. An output interface converts the stored voltage into the analog form and then outputs this to the actuator circuitry. This, of course, would require the value generated to be written on a register. In an output, in order to produce an analog output, the CPU selects the data register of the output interface and writes the necessary data to it. The two main functional blocks of an output interface are D2A register and D2A converter. The interface takes care of buffering and handshake control aspects. Analog to digital conversion is frequently deployed in an input interface. Similarly, digital to analog conversion is frequently used in an output interface. So, this is the basic model of a real-time system. You can design basic model keeping in mind these basic concepts. So, now we can discuss the characteristics of real-time systems. So, what should be the characteristics of the real-time systems? We have seen the applications of real-time systems. We have seen the basic model of real-time system, how a basic real-time systems looks. And now we have come to the point where we can discuss the characteristics of real-time systems. Different characteristics of the real-time systems are that time constraint, new correctness criteria, embedded safety criticality, concurrency, distributed feedback structure, task stability, custom hardware, reactive stability, and exception handling. So now we will discuss these characteristics one by one in a brief manner. That is time constraint. Every real-time task is associated with some time constraints. One form of time constraints that is very common is deadline associated with task. A task deadline specifies the time before the task must complete and produce the results. Other types of timing constraints are delay and duration. So it is the responsibility of the real-time operating system to ensure that all the tasks meet their respective constraints. Next characteristic is correctness criteria. The notion of correctness in real-time system is different from that used in the context of traditional systems. In real-time systems, correctness implies not only logical correctness of the results, but the time at which the results are produced is very much important. A logically correct result produced after the deadline would be considered as an incorrect result. Next characteristics is embedded. A vast majority of the real-time systems are embedded in An embedded computer system is physically embedded in its environment and often controls its of embedded system that we often refer to as system, as we have discussed in example 6. Next characteristic is safety criticality. For traditional non-real-time systems, safety and reliability are independent issues. However, in many real-time systems, these two issues are intricately bound together, making them safety critical. So, it must be noted here that safe system is one that does not cause any damage even when it fails. The system, on the other hand, is one that can operate for long durations of time without exhibiting any failures. A critical system is required to be highly reliable, since any failure of the system can cause extensive damage. That a new technique or formal methods is used to design a safety critical systems. If time permits, then I will discuss formal methods, why they are used in the safety critical, because my research area was on formal methods. I have done my PhD in. So, if time permits, I will discuss in length on the safety critical systems and use of formal methods in safety critical systems. Next is concurrency. A real-time system usually needs to respond to several independent events within very short and strict time bounds. For instance, consider a chemical plant automation system. Correlate the examples with the characteristics of the real-time system. That's why I have discussed the examples in the start, and now the characteristics of the real-time systems are kept for the later part of the presentation, so that you can correlate characteristics with the real-time systems which are available in the real-life applications. So, in concurrency characteristics, a real-time systems usually need to respond to several independent events within very short and strict time bounds, as we have seen in the chemical plant automation system, which monitors the progress of chemical reaction and controls the rate of reaction by changing the different parameters of the reaction, such as pressure, temperature, and chemical concentration. Parameters are sensed using sensors fixed in the chemical reaction chamber. These sensors may generate data asynchronously at different rates. Or the real-time systems must process data from all the sensors currently. Otherwise, the system may malfunction. Those systems can be considered to be non-deterministic, since the behavior of the system depends on the exact timing of the inputs. In non-deterministic computation, one in which two runs using the same set of input data can produce two distinct sets of output in the two runs. The next characteristics real-time system is distributed and feedback structure. In many real-time systems, the different components of systems are naturally distributed across widely spread geographic locations. In such systems, the different events of the arise geographically separate locations. Therefore, these events may not may often have to be handled. Response produced to them to prevent overloading of the underlying communication networks. Therefore, the sensors and the actuators where events are generated. An example of such a system is a petroleum refinery plant over a large geographic area. At each data source, it makes good design sense to locally process the data before being passed on to the central processor. Also, many distributed as well as centralized real-time systems have feedback structures. The next characteristic is task criticality. The task criticality is a measure of the cost of failure of a task. Task criticality is determined by examining how critical are the used by the tasks to the functioning of the system. Real-time systems may have tasks of very different criticalities. It's natural to expect the criticalness of the different tasks to consider while designing for fault tolerance. The higher the criticality of a task, the more reliable it should be made. Further, in the event of failure of highly critical tasks, detection and recoveries are important. However, it should be realized that task priorities is a different concept and task criticality does not solely determine the priority on the order in which various tasks are executed. Custom hardware. A real-time systems is often implemented on custom hardware that is specifically designed and developed for the purpose. For example, a cell phone does not use traditional processor. A cell phone uses processors which are tiny, supporting only those processing capabilities that are really necessary for phone operations and is specifically designed to be power efficient to conserve battery life. The capabilities of the processor used in cell phone are substantially different from that of a general purpose processor. Another example is the embedded processor in MPI car. In this case, the processor used need not be powerful general purpose processors such as Pentium or ARM processor. So it is the custom hardware which is needed in the real-time systems. System the next characteristics which the real-time systems are reactive. Real-time systems are often reactive. A reactive system is one in which interactions between the computer and environment is maintained. Or systems compute functions on the input data to generate the output data. Other is stability. Under overload condition, real-time systems need to continue to meet the deadline of the most critical task, though the deadline of non-critical task may not be met. This is in contrast to the requirement of fairness of traditional system, even under overload conditions. And last characteristics, which I mentioned here, is exception handling. In many real-time systems, work round the clock and often without human operators. For example, consider a small automated chemical plant They to the work non-stop. When there are human operators, taking corrective actions on a failure become difficult. If no corrective actions can be immediately taken, if failure does not result in catastrophic situations, it should be detected and the system should continue to operate in a gracefully degraded mode rather than shutting off abruptly. So now we are remaining 10 minutes. So I will simply type of real-time task, that is what is a hard real-time task, what is firm real-time task and soft real-time task. And after that, simply cover the safety and reliability. Why formal development is important for safety critical systems. With this, I will conclude my talk. I will in next 10 minutes. Because I think all of you know what is hard real-time task, what is firm real-time task, and real-time task. Can anyone tell what is hard real-time task? Hard real-time task is one that is constant produce its result within certain predetermined time bounds. The system is considered to have failed any of its real-time task does not require results before the specified time bounds. And a system having hard real-time task is a robot. So what is firm real-time task? Every some predetermined line before which it is required to produce its result. However, unlike a hard real-time task, even a firm real-time task does not complete within its deadline, the system does not fail. The list is discarded. That is, in other words, the utility of the results computed by a firm real-time task becomes zero after the deadline. And soft real-time tasks also have time bounds associated. The timing constraints on soft real-time tasks are not expressed as an absolute value. Instead, the constraints are expressed either in terms of the average response time. Example, we can quote an example of a soft real-time task is web browsing. Normally, after an URL, it name the full form URL. Anyone from the participant can give the full form of you. Yes, hello. I got the so after an URL that is uniform resource locator is clicked, the corresponding web page is fetched and displayed a couple of seconds on the average. However, and it takes several minutes to display a requested page, we still do not consider the system to have failed, but merely express that the performance of the system has degraded. Can you also mention discussed earlier? This can be kept in the soft real-time category. From the participant, can you mention the example which I have discussed in the category of soft real-time system category? We have 12 examples, and one of or more than one of them have fallen in this category. Can you name which one fall in the category of soft real-time task? So we can keep a seat reservation system under this category, because once the request for the reservation is made, the response should occur within 20 seconds on the average. And this response may either be in the form of printed ticket or an apology message on account of unavailability of the seats. Alternatively, state the constraint on the ticketing task, as at least in the case of 90% of reservation. Request the ticket should be processed and printed in less than 20 seconds. So, is there a real-time task which can be used in the real-time category? Can you think of any example of non-real-time task? Okay, email. Any other example? I can mention a few of the non-real-time tasks: batch processing jobs, email, background tasks such as etc. The types of real-time tasks. As far as the safety and reliability are concerned, there are many techniques and software to maintain the safety and reliability of the system. And method is one of the techniques which are used to ensure the systems. So you can read this slide. I am not going to. You can see that for any development of software for real-time systems, ensure the reliability and dependability. So now it becomes are considered in the design phase itself. That the cost of software is one of the issues. Use testing and maintenance cost becomes, if it is detected in later phase, it's very. The new design techniques are developed where these issues are considered in the design phase itself, and formal development technology and methods are one of the design techniques which ensure the safety and reliability of such safety critical systems. So that's all from my side. If there is any question, I am ready to take it. Otherwise, I will share this slide to Brijesh and he will give it to participant if they needed it. Thanks. Thanks from my side for listening to me and organizer to give me the chance to talk in this FDP.
Thank you so much, sir. It was a very elaborative session. We thoroughly enjoyed the entire session. I would request our respected director